4473, and it's actually listed with CS 5473. So we half of you are undergrad students, and half of you are graduate students. I'm Changgo Pan, so I'm an associate professor with computer science, but I also have a joint appointment with microbiology, plant biology. I came to OU in 2018, so I taught this course in last spring semester, so this is the second offering. Before I came to OU, I worked in Oak Ridge National Lab for 12 years. So over there, I'm in computer science and a mathematics division, so primarily working on high-performance computing for bioinformatics applications. So in RNL, they actually built the largest supercomputer in the world, which is called a Summit supercomputer. It's made up of thousands of computer nodes. Each node has 4 GPUs and 2 CPUs. So we worked a lot on research on parallel computing for all kinds of scientific application. So I think this is a very exciting topic. So we will learn the basics of how to do parallel computing, distributed computing. My office is in Devon Energy Hall, 231. And this is my email address. If you have questions, feel free to email me. And also, you can also use a Canvas message. So that's probably easier for me to organize all the emails this course. So we will use extensively all the functionality of Canvas. So make sure you check Canvas regularly. So we'll release all our homeworks and quizzes in Canvas. My office hour is from 3:30 to 4:30 on Mondays. So it's right before this class. So if you have some questions, so feel free to stop by my office before the class. So I'm happy to discuss those questions that you may have. We will have a TA. His name is called Abnash. So he is a second-year computer science PhD student, and he has been TAing for other courses for a long time, like Introduction to C Programming. But this is the first time he is TAing for this course. But I think he will do a good job. He took this course in last semester, and he got an A on this course. So for the office hour, he will do that in Devon Energy Hall 115. And his office hour is from 3 to 4 on Thursdays. And also you can email him to this email address, or you can contact him on Canvas. So also, we are open to meetings by appointment. So if you have some questions, feel free to schedule an appointment with us if you cannot wait until the office hour. So first, why do we need to learn parallel distributed network programming? So this is actually a very broad topic, but it's primarily driven by the same trend. So this is a chart of the microprocessor from 30 years ago to a few years ago. As you can see that the Moore's law is still alive and well. So the number of transistors per processor has been able to increase exponentially. So this is linear time, and this is exponential scale. So it has been held on pretty well. I think this trend will continue for the next decade or so. But what has been changing just last year is the single thread performance in here. So you can also see it on this screen here. So what happened is that this, if you write the same program, and you can count on in 2 years later, your single thread program will run twice as fast, just because the hardware is becoming faster. But around 2010, this trend has to reversed. The single thread performance of the program is plateaued. It's not because we have less transistors to spend on a processor. It's primarily because we are limited by the power. There's only a limited power we can put into a processor without it being overheat and melt down. So as a result, we also see the frequency of CPU has plateaued. So you cannot count on the CPU will become faster and or become higher performance with pipeline and other tricks that you learned in OS. So what has all this new transistor been invested into? Is that being invested into the number of cores. So imagine you're Intel or AMD. You have all these transistors, you can put on a chip, but you cannot put it into a single core. So instead, you have to put into 2 cores, 4 cores, or 8 cores. So the number of cores has increased dramatically. So now if you are a programmer, if you are a software engineer, and you have a single-threaded program that you can run on a single-core CPU, then you are asked to make the program run faster. So this is a computing-bound problem. There are two approaches. One is you can make your algorithm more efficient. So you have learned all this algorithm optimization on your other courses. So this is of course hard. If you want to squeeze out 10%, 20% actual performance on a serial code, that's a lot of hard work. Or you can compromise your results accuracy and do a heuristic algorithm. So alternatively, you can take advantage of all the extra cores available on the CPU and do a multi-threading program. So this is one problem, that's a computing bound problem. Or you have a problem that you need to process a lot of data. And this is constrained by the memory available on a single computer. Again, you have a lot of tricks to make your data more memory efficient. For example, you can use more efficient data structure, or you can figure out a way to stream the data from your hard drive and to the memory. This all has some compromises in the performance. As an alternative, you can think about distribute your program across many, many computers. All these computers have between 10 to 100 gigabytes of memory. Then you just need to worry about how do you coordinate the computation across all these computers on a network. So this is a two-type problem where you really need to think about how do you distribute your computing across computer or across different cores on the same computer. So this is the hardware that we're going to be talking about in this course. So one is the CPUs. So this is actually a mainstream desktop computer. Unlike 10 years ago, right now, even desktop computer has multiple computer cores. So this is a i5 Intel CPU. So you can see that it has 4 cores here, and all these 4 cores share a L3 cache. And we'll talk about how do you consider the cache coherence across all the cores. So again, if your program only uses a single core, so you are wasting all the computing power sitting on the other cores. And you can use the OpenMP program to speed up your code just by making it run in parallel across all the cores. So right now, CPU can have up to 16 or 32 cores. But on most desktops and laptops, you have an even more powerful processor. It's called a GPU, Graphic Process Unit. Originally, it's developed to speed up your image processing or to process a huge amount of video data from the games or other video applications. But now, NVIDIA actually exposed the API to their GPU. You can actually run general purpose application on GPUs too. So GPUs are very powerful for numeric calculation, but so this is because it actually has thousands of small cores. So if you think 32 cores on CPU is a lot of cores. On GPU, you have thousands to tens of thousands of cores. Of course, those cores will be slower individually, but together they can give you a lot of throughput to process a huge amount of data. So this parallelism is even more massive than the parallelism you will see on a typical multi-core CPU. Of course, it also has a lot of constraints. Basically, Intel and NVIDIA has the same access to the same hardware technology. The reason why you can pack this many CPU cores, GPU cores in this kind of chip is because they sacrifice in the memory access. For example, GPU doesn't have so much L3 cache, and it also can have very simple control unit. When you are trying to write a program for GPUs, there's additional hardware consideration. So now suppose your program runs well on a single desktop or a single laptop, but you still cannot have a control over how much computing power a user has on their own laptop or their own desktop. So alternative ways to move the computing over a server in the cloud or in some kind of data center. So you can have exact control over what kind of hardware do you have on the server, and you can do the same multi-threaded computing or the GPU powered computing on the server. Then your program will expose the input and output through an internet to the client. For example, we all have used cell phones to do all kinds of things, like even you do a Google search. Basically, you are sending a message to a server on the Google's data center and it sends results back. Your client essentially becomes an I/O device. To allow this kind of application, we need a network programming. Basically, that's about how do you do the communication between a client program and a server program. And this is another form of distributed computing between two different computers. Of course, you can do your computation on a single server. Lots of times, that's still not enough. So then what you do? So you actually can run your program on a cluster. So this is how it looks like. Each cabinet here may contain 10 to 20 different computer nodes. Each node may have multiple CPUs and multiple GPUs. And this is a massive parallel computing. And to program this kind of computer cluster, we need to learn MPI programming. So in that case, you are trying to coordinate the computation across many nodes. And they will have very high-speed interconnect, so they can send a message to each other. And also, you can use a different programming model called distributed programming. In that case, some communication is hidden from you, and you can use a higher level programming model called MapReduce. In that case, you just need to write a map program and a reduce program, and you don't need to worry about all the lower level communication. Of course, this is better to suitable certain problem that can be fit into a MapReduce paradigm. So if we put all this together, this is about PAND programming. So we'll expose the parallelism on supercomputers on the client computer or server, and we'll learn network programming. How do you communicate between multiple computers through internet? And we'll learn how to use cloud computing and supercomputers, and run MPI jobs and MapReduce jobs on a data center or supercomputing center. So after you have learned, you will find that many of these real-world applications are powered by this kind of different parallel applications. Of course, the classic ones like Microsoft Office, I don't think is parallelized, but there are also other applications like internet browsers. For example, if you open a Chrome, when you open a new tab, Chrome is actually use a new thread to handle that new tab. If you have opened like 20 to 30 different tabs to browse different websites, so Chrome is actually using 20 to 30 different threads to handle the computation. So in that case, it can take advantage of the full course or a course on your laptop to speed up your computation to browse faster. We talked about this Google search. So imagine in your fingertip, you can query all the data on the internet. So actually, that's a very powerful thing to do. It's not powered by your laptop or your phone. It's actually powered by Google's data center that houses millions of different computer nodes. And that's implemented by using MapReduce. And when you use Google Apple Siri, you speak to your cell phone, and cell phone is sending data over to Apple's server. So the voice transmission is done with a network programming application. And now the server side, you are expecting the Siri to talk to you in real time. Even if you have a millisecond delay, you will notice that. So in that case, how does Apple to convert your voice signal to a sentence? So that's done with GPU. So you have to process those massive amount of data, run machine learning on it, and then give the results as quickly as you can. And finally, for the Netflix, you can watch all the shows. Of course, you need a data center to store all the content in your computer center. And again, this will be more like a memory-bound problem. It's only because you have access to all the computers in a data center that allows you to downstream the data from any shows in the Netflix library. So finally, in scientific computing, that's where I'm working on. A lot of science problems are now being tackled with a massive amount of data. So if you look at biology, physics, astronomy, so scientists are acquiring huge amount of data. And those data are being solved on supercomputers, so with tens of thousands of computer nodes. So all this requires the new generation of software engineers to know how do you parallelize a program, and how do you think in a parallel mindset. So this is about an overview about our course. So let's then talk about the logistics. So first, so you should bring a laptop to the classes and the exams. So in the class, we'll do in-class exercise. If you check the Canvas, you can probably already see that I have released an in-class exercise as a quiz 1.1.1. So if we can get to that point, we'll do that. So in most lectures, we will have between 1 to 2 in-class exercises. So it's mainly to help you to use the information you just learned, and then you can practice a little bit more. And also, we will do the exams using Canvas. So you don't need to check that right now. You can go home. If we get to the exercise, I will give you time to get to know like how do you use a Canvas quiz to enter your answer. So the exercises are mainly formulative. So we are going to mainly look at did you spend effort into work on the problem. So we are not going to grade for the correctness. So this is the computing in the class. Then you should also get a user account in the Schooner supercomputer. So this is the environment where you will do most of the OpenMP programming and MPI programming. So you should watch out for Canvas message from Abinash. So we'll send you a user account with a password. So user number will be just 1 to 100. So we'll just assign you a random user account. And once you can do all your code testing on the Schooner. So when we grade your code, we also run it on the Schooner. So since we have the same computing platform, so it should be easy for us to evaluate your program's performance. We're also going to use Google Cloud Platform or GCP for the distributed computing part of this course. So we have applied for student credit from Google. So we will assign you a user account. So you should be able to register for a free account using your OU email account. Then you should have $20 to spend on any Google Cloud service. So we'll give you some assignment. So you are supposed to do your development on GCP and then turn in your homework assignment. So again, watch out for a Canvas message. So we'll give you more instruction about how do you set up your computers and how do you work on the problems. So for any questions about this computing environment? Okay. Programming language. So since you guys all are senior undergrad students or PhD students, I assume you have all learned the basic programming in Java or C or some other languages. In this particular course, we are going to use Python and C. So right now, you should just refresh your memory about Python and C. So this is basically two extremes of a programming language, a very low-level language and a very high-level language. And for Python, you mainly need to refresh your memory about how do you do a high-level programming, like what's a list, what's a tuple. So this is all data structure that we will use in the network programming part. With C programming language, it's simpler, but you have to refresh your memory about how do you do the memory management. For example, malloc array. So for example, C doesn't give you a multi-dimensional array. You have to flatten out your multi-dimensional array to one-dimensional array. How do you work on that? So refresh your memory about the C memory management and data structure. With Python programming, we will mainly use it for software programming. That's section 1. And we will also use Python for the last section, that's MapReduce programming, section 5. With C programming, we'll use it for the MPI programming, which is section 2, and OpenMP programming, CUDA programming in the middle. This is the schedule of this course. As you can see, we have a lot of topics to cover. So each topic only have a small section in this course. In the first section, we'll talk about computer networks. So we'll use the internet as an example. In this section, you will mainly learn how do you do software programming. So remember, we'll do do this exercise in Python. We will use about between 3 to 4 lectures to cover network programming. So I hope I can get a head start on the network programming part in today's lecture. After we learn how to do socket programming, then we'll switch our focus to MPI programming. So we'll spend about 7 lectures on this topic. And this is where you are going to start to use Schooner supercomputer at OU. For this part, you will do the socket programming on your own laptop. We have already set up a server program sitting on a Google's cloud system. So you can talk to our server program on the Google Cloud. Okay, section 3 is about MPI programming, OpenMP programming. And we'll spend 6 lectures on this. So actually this lecture is more important because you may not need MPI programming for your particular application. But if you don't do MPI programming or other kind of multi-threading, you are wasting all the computing power of this multi-core CPUs. So next, GPU programming. For that, we'll teach you how to use CUDA. So that's the most popular GPU programming model. And we'll spend about 5 lectures on this. So finally, we'll zoom out again. So we'll talk about distributed computing. And this is about how does Google give you all this computing infrastructure as a service. You can spin up a virtual machine. You can spin up a virtual machine cluster. And you can do MapReduce programming with those infrastructure. And we have about 3 lectures to cover that. So as you can see that, if you look at each of those topics, that can be a topic for a course that lasts 1 semester or 2 semesters. So with MPI programming, people have been spending a PhD on that. So of course, here we cannot teach you to become an expert in any specific topic. But here we want to give you an introduction across all the topics. So this is my expected learning outcome. So first, I hope you can gain a conceptual understanding of all these parallel programming models. I think all of you guys have learned Java programming in the first year. Right? In the first year, you learned how do you write a program, how do you declare a variable, and how do you write if statement and for loops. Essentially, we're going to do all that, but with a parallel manner. For that, how do you parallelize a for loop? What if you have a if statement? How do you handle that in a parallelized fashion? So basically, a conceptual understanding of the hardware and the software constraints. And then some basic programming model, like how do you send messages between different processes, different computing threads. And this is mainly about syntax, like how you learn in Java 1, how do you use different syntax to declare a class, how do you declare a method inside a class. And finally, we'll talk about some exemplar problems. So this is a very simple problems, like how do you do a sort in a parallel fashion. But I'm sure in the algorithm analysis, you learn a bubble sort in a serial fashion, right? So here we'll learn how to do it in parallel fashion. How do you count words in big text in a parallel fashion. So basically, this is all kind of simple, but a very representative problem that you can use in the future to give you a good understanding of the concepts. Of course, what we won't have time to cover is parallel design patterns. Like if you solve a parallel problem for 10 times, you can start to see common characteristics. Like they all share something, like you all need a manager to manage a few across the workers. And they can use a halo exchange to solve a whole class of matrix multiplication problems. For that, you really need to be exposed to many, many different problems and let you to summarize this is a common characteristics across all those problems, like graph theory problems. So think about this as algorithm analysis and software engineering that you have taken in your senior year or junior year. So this is based upon where you have already learned the basic programming skills. Unfortunately, we will not have time to do that, to cover all that. So we will only kind of cover the basics. And also performance optimization. So one of the experts said it's easy to write a parallel program, but it's hard to make it perform well. So performance optimization for parallel program is one order of magnitude harder than optimizing performance of serial program, because you have to think about many, many threads and how to coordinate them. So we'll cover very little about this topic. So This is just to give you a sense about what we all learned, what we won't have time to cover. So in the last time, I got a complaint about this course being too easy. So because they are expected to learn this, but I'm just trying to shoot the middle ground. So it should not be too hard for you to not be able to catch up. At least, but at the same time, it's gonna be hard because we're gonna change how you think about computing. So from now, you only need to think about it. You have multiple threads, multiple processes that's working for you. But you can do that if you have the good foundation. If you feel that you need more material, or you feel that you need additional help to digest the material that we covered in the class, feel free to read these textbooks. So as I mentioned before, each topic is can be a course by itself. So that's why each topic we have a separate textbook. For example, for the computer network, this is a very classic computer networking textbook. It has been around for a long time. And we are only going to have time to talk about the first 3 chapters. But this is where you need to be able to do some basic circuit programming. For the OpenMP and MPI programming, we'll primarily use this textbook, Introduction to Parallel Programming. And we'll add some material from this textbook as well. This is the more recent, add some more fresh materials. So we'll probably cover most of the material in this textbook about MPI programming and OpenMP programming. So next, we will use this type of programming massive parallel processor, a hands-on approach to talk about GPU programming. So again, we only have the time to talk about the first 3 to 4 chapters. I think it also gives you a good overview about what does it take to do GPU programming. And we'll also use some exercise and lab material from this textbook too. For the distributed computing, it's a relatively new topic, and I haven't found a good classic textbook. So this course will be mainly combining the material from these 2 different textbooks. So one is more practical to teach you how to use the Google Cloud computing platform. So some of our lab exercises and homework assignments will be based on this. For the theory part, we'll use this textbook, Distributed Cloud Computing. So it's actually published a number of years ago. So we'll basically do an in-depth, deep dive into this book, then a survey of the chapter from the other books. Then, any additional question about the textbooks? It's recommended, it's not required. So if you feel that, I feel that I can cover most of the material in this book. Oh, the other thing is, I use a lot of slides from these books, so I'm not going to give you credit and acknowledgement for each individual books. So usually, if I present a section, the slides, lots of the slides figures will come from those textbooks. And this is a tentative schedule. So today is about an introduction. Then the next couple weeks, we will cover the computer networks, and we'll have the first homework assignment about computer networks. Then followed by MPI programming. So in MPI programming, we'll have 2 homework assignments. Then we'll have our exam 1. So this will cover these 2 topics. So next, we'll cover OpenMP programming. And also, again, we'll have 2 homework assignments on this topic, followed by exam 2. So all the exams is comprehensive. That means exam 2 will cover the material covering the previous 3 topics. And the last part is GPU programming and distributed computing. We'll have 2 homework assignments for the GPU programming and 1 for the distributed computing. Then in that week, we'll do a review and a question Q&A. Then we'll have a final exam. So in total, we'll have 3 exams, 8 homeworks. So although I gave the schedule here and in syllabus, these lectures are actually subject to change because it's very hard to control the pace of the lecture when I have the in-class exercises. So expect to have a variation plus minus 1 lecture in these weeks. But the schedule of the exams are fixed, so you should definitely plan to block those times. Make sure you are coming here to take the in-class exams. So I'll release the slides and the in-class exercise to Canvas beforehand. So, but they are released in the unit of chapters, not by the lectures. So some lectures will cover more than one chapters, but more likely we only be able to have time to cover a part of it for a chapter per lecture. For the homework, we'll give you a due date in the Canvas. If you are 1 day late, we'll penalize, give you a 10% penalty. 2 days, 20% penalty. Then you get a 0 point if you submit after that. So pay attention to the due days. And of course, the in-class exercise is a very important component of this course. So I know some of you guys will have problems in some courses with some classes. For example, you have doctor appointments. So if you know you're going to miss a class, just email me or Abhinash beforehand. And you should be able to, you should complete the in-class exercise within the same day or before that to get the points of the in-class exercises. And this is the evaluation. So in-class exercise count for 15%, and the homework will count for 50%. So I know a lot of courses separate they have a separate lab assignments and homework assignments with more theoretical question. In our course, homework will made up for both the programming problems and the theory problems. So we don't have a separate lab assignments or projects. So everything is supposed to be in the 8 homeworks. And then we have 3 exams. Finally, I want to cover the academic honesty. For the in-class exercises, it's supposed to be interactive. Feel free to discuss with other students in the class. So it's mainly to help you to learn, basically to give a refresher memory about what we just covered in this course. However, for the homework, you're supposed to only independently. So you're not supposed to get help, give help, or get help from any other students. So you can use lecture slides, textbook, or other online material as references, but you cannot just copy code. So if you should not try to like Google code, then just make some trivial change and turn it in. So this is not acceptable. For the exams, I don't want you to guys spend a lot of time to memorize the syntax, like how to send a message between 2 different processes. Actually, you have 8 different parameters. Sometimes it can be hard to remember them in the right order. So in that case, you can bring 2 sheets of reference paper with you. So before the class, you should refresh memory about what you have learned in these past few lectures, and then just write it down. So writing the notes itself is a way to help yourself to review whatever you've learned in these past few lectures. And then you can bring this paper with you. But in the class, in the exam itself, you are not allowed to use other references. For them, you cannot Google, you cannot look up any textbook. And finally, of course, you cannot get any help from other students in the exams. So if you find academic dishonesty, so the penalty is 0 on the exam or the assignment. At the same time, we'll file a report to the academic misconduct to OU. So OU handles, in this case, I and Avinash are only the witness. Basically, we found a suspicious behavior, so we just report it. If you want to contest that, you don't need to come to us. You should contest with the OU misconduct office. They will evaluate your special situation and then make a decision. So we are happy to accept their decision. So here, our job is to make sure we are being fair to all the students. So no one should gain a unfair advantage over other students. Okay, so this is the logistics and an overview. Any questions so far? Yes.
On the 2 pages of notes for the exam, is that like 2 physical papers front and back, or 1 paper front and back?
It's 2 pages, so you can use 1 sheet of paper front and back. And also don't forget our lookout time. If you bring out too much material, you can spend a lot of time to search, and that's expensive. so we have about 40 minutes, 45 minutes to actually cover some material in the first section. And you will probably start to notice that the numbering scheme in our canvas. So we have 4 sections, right? So it's numbered the first digit. Then each section have chapters, and then after that we have one more digit to designate which specific section subgroups, like for exercise. So here we are in section 1, chapter 1. And this is the textbook that we'll be using. We are only going to be covering the first few chapters. So we start from chapter 1. We will start with an introduction. So here, this is the topic we are going to cover. So first, what is the internet? What is protocol? And what are the internet network edges, hosts? And you can see that we spend a lot of time on the terminology. So when you're learning a new topic, being able to learn the speaking the right language is very important. So you know there's a famous saying in computer science, there's 2 most difficult challenges for computer scientists. One is the cache coherence, the other one is naming things. So computer science often comes with different names for the same thing, or have the same name for different things. So it's very important for you to learn the language of network programming. So we'll give you a clear definition about all these terms you're going to see here. What is a packet, what is a circuit, and what is loss, and how to define delays. So we'll cover all these basic concepts so you know all the conceptual framework in network programming. And this is a roadmap of this chapter. We will have 5 different sections. We'll start from the first one. What is the internet? So first, internet is made up of billions of connected computing devices. And this is all the examples. So you can think about cell phones, servers, and laptops. They are all kind of hosts for internet. So internet actually doesn't discriminate between servers or cell phones. To the internet, they are all hosts for an end system or endpoints. And all these hosts will run applications on top of it. Since they all can be communicated with each other over the network. So we call these computer programs as network applications. So in fact, in this homework, you'll learn how to write a network application yourself, a very simple network application. Then we have communication links to connect all these hosts together. And these communication links can be in different forms. Like say you have a cell phone, so you will be communicating with other host by wireless network. If you have a server, so this server will most likely will be plugged into an Ethernet. So they will be communicating through a wide connection. And all these big servers on the network inside here, they are connected through fiber. And these are all called communication links. Then finally, we have packet switches. So there are 2 types. One is called routers, the other one is called switches. So these routers are like a post office. Their job is to sort the message going from one host and direct it to the next sorting facility and the next one until it reaches the destination. So you should remember these 3 components. You have the host, you have the links connecting the host to routers, and the routers will connect all these hosts through a communication channel. So what makes the internet different from any other network? For example, before we have a network within a home or a computer organization. Internet is different because it actually is a network of networks. These networks are connected to each other by this ISP, Internet Service Provider. So they have to make sure all these networks can talk to each other. And then if these networks are using different languages, it's like if you run one program in C, the other program in Python, how do you make them talk to each other over the internet? So this is accomplished by a protocol. As long as the 2 programs agree on a common format to send a message to each other, actually they don't care about what the language or what kind of format is running in the other end. They just need to analyze the message received, and according to the format that's agreed by the community, For example, you probably heard a lot of terms like TCP, IP, and HTTP. These are all different internet protocols. Then what services are provided by internet? You can think about the internet as an operating system. You can, just like operating system in a single computer, for example, you allocate memory, the operating system will provide that for you. The detail of allocating memory is hidden from the programmer. Similarly, in the internet, it also provides service to the network application to send messages. You just need to write a line to open a port to send a message to a distant server. The internet will provide service to you to send the message to a server. And also it will provide a programming language. That's basically the API for the internet. So for example, how do you send and receive messages? How do you make sure that message to receive the right destination? So these are all the services provided by the internet. Then the second part of the internet is the protocol. Let's make an analogy with a human protocol. When we try to communicate with another person, usually we have a agreed upon protocol. And for example, we can start with, we want to ask a question, what's the time? So we probably don't want to ask this question right away. We have a certain way of establishing a communication channel. Similarly, when you try to communicate over the network, we also define a set of network protocols. But this protocol is designed for machines instead of humans. Basic protocol defines the format and order of messages sent and received among network entities. And this also specifies what actions the host can take on these messages. Let's take an example. Let's say we have two humans, they want to get some information. And let's say this Alice wants to get the time from Bob. If Alice just asks her, what's the time? Then she may not have the attention of the Bob beforehand. So maybe that message is lost. So maybe the Alice should first say hi to Bob first. Then the Bob will hear that hi, then he's supposed to give a response back. Then only after Alice hears a response from the Bob, then Alice can ask the time. If Alice doesn't hear a response from the Bob, a response hi, that means the Bob may not be paying attention, maybe Bob is busy. And if Alice sends a message beforehand, then again, that may be went unresponsive to the Bob's side. So you can see this is a protocol that we establish when we ask the time between two humans. Two machines, we can also establish this kind of protocol. For example, in TCP protocol, we have two computers that want to talk to each other, a client and a server. The client may first send a request to establish a connection. The server may respond to grant that permission to establish a connection. Then the server may ask, the client may ask the server to give me a certain file. Then the server can give that file back to the client. So this kind of behavior needs to be standardized. So the programmer on the client side can write its own programming, client program. Like say you can use Google's Chrome or Firefox. They're all different kind of client program. But as long as they write to the same protocol, they can both talk to Facebook's server program. And similarly, on the server side, you may write a Google internet search application, or you may write a Facebook application. You don't care really what kind of browser sends the message to you. You just write to this kind of TCP/IP protocol. So this simplifies the development of a network application. And at the same time, that means you really need to learn network application before you can develop your own applications. So here we have to give you a very quick overview of what is the internet. Then we can dig into the different components. What is the network edge? What is the network core? You can think about the network edges as the host. So basically, if you have a laptop or a cell phone, you can think of that as belong to the edge of the network. And it may not be intuitive to you, but the servers are also considered the network edge. Let's say if you have a Google server. To the internet is just another host. It's also considered to be the edge of the network. It's all the same to network. The core of the network is actually the routers and the communication link among those routers. And then the network edges also have the access network. So here we're talking about the Wi-Fi. For example, if you use a laptop now, so you're connecting your edge towards an end system link to the server through a Wi-Fi connection. If you have a server sitting in a data center, the server needs to be connected to the router through an Ethernet or fiber. That's also considered an access network. The core are the routers in the network, so those will be invisible to the host. Then how do we connect the end system to an edge router? So we can have a different type of end points. One is a residential access network. For example, if you have a network at home or in your apartment or in your office, this is considered an end system network. At home, we also use Wi-Fi to do the connection. And as institution networks, they also provide an Ethernet wide connection. And also your cell phone would be access internet through this mobile access network, for example, 5G or 4G networks. When we are talking about these different networks, when you're doing the network application development, actually you don't need to worry about how the bits are actually sent over the wire or through the air. What you need to care about is really the bandwidth. So that's measured by bits per second of the access network. And also you need to remember if this link is shared or dedicated. If you have a shared communication link, that means if there are many people going through the same communication chain link, you will have a congestion in your network. So this is also a consideration to think about when you handle the network congestion issue. So for us as a network application developer, we need to worry about the transmission rate. And another term for it is the bandwidth. You probably also heard about this. For example, when you try to call Comcast, they will try to sell different type of cable service. And they will distinguish it by different bandwidths they will offer to you. Typically, larger bandwidth will carry higher monthly charges. So what does this transmission rate mean exactly? It's often defined as a bit rate. It's very simply defined as the number of bits that can transmit it over a communication link per unit of time. So oftentimes this is defined as a bit per second. So it's pretty intuitive. That just means if I have a communication link to you, how many bits can you push into that communication link per minute, per second here? The symbol is a bit per second. So oftentimes we'll hear this bit per second is too small. We need a larger unit. And this is one very confusing point. When we try to quantify the bandwidth or transmission rate, we use the decimal prefix. For example, when we talk about a kilobit per second, it actually really means just 1,000. It's not a 1024 bit per second. So this is a key point that I often get confused when you're used to working in other computer science area. In network, for example, when you say megabit per second, it actually really just means a million bits. It's not a 2 to 20 bits. So if I ask you to do a computation about how fast, how many bits do you need, for example, I can ask you to transmit a million bits over certain communication with certain bandwidth. Remember to do the conversion, use the decimal conversion. So of course, this if you don't use the binary prefix, then usually you have this I after the K. For example, if it's using the binary, so it's ki bits second. If it's megabits per second, it's MIBIT. So pay attention to this. But most people use the decimal prefix. In addition to bits per second, some people also use bytes per second. In that case, you will see this uppercase B here, then /s. So you can see this is distinguished primarily by lowercase and uppercase of this B. Of course, if you use 1 byte per second, that means 8 bit per second. So again, make sure about this unit conversion when you're trying to calculate the transmission rate. Similarly, when you use the byte per second, also make sure to know that it's also a decimal point prefix. For example, if you have a kilobyte per second, that just really means 1,000 bytes per second. So pay attention to this. We will have you in-class exercise to ask you to do this kind of conversion. So you will go to that point if you use different, you're confused between 1,000 and 1024. So let's say you have this access network at home. What are the components? First, if you call Comcast, it will ask you, you should have a cable in your house or your apartment already. That cable connection goes to the Comcast central office to a router that will route to the internet, the core internet, the internet core. Then after you have a connection, you need a cable modem or DSL modem. DSL primarily work with the phone lines. This modem will convert analog digital signal and analog from and to each other. The signal on this cable is analog, but actually you send a digital signal over this internet connection. The modem will do that conversion for you. The modem will connect to a router. So the router allows you to connect to multiple devices in your home. So for example, if you don't have this router, you can still connect your laptop or desktop through a Ethernet cable to this modem. But that means you can only connect one device to this network. So if you want to have multiple devices, you need a router. This router will do this message forwarding, make sure all they can have a fair share of access to this connection. You can connect a desktop to this router through Internet, or you can use a Wi-Fi to connect all the other wireless devices. Typically, when you buy something from Best Buy, the router actually are combined with this Wi-Fi router. So this is the same device. Okay, so we just talked about transmission rate, right? And also just talked about bandwidth. And then we need to quantify that. So if you have a wireless access network, you can use Wi-Fi. Wi-Fi actually comes with a different definition, different protocol. So you have 802.11b. So that only have 11 megabits per second of transmission rate. If it's G, that's 54. If it's N, that's 450 megabits per second. So this is typically, if you go to Best Buy, you should look at a different browser, or just go to Amazon and search for Wi-Fi routers. They will give you this specification as performance rating on the router. Of course, this is only the access point. Your actual transmission rate is still limited by the transmission rate allowed in your modem or the Comcast allowed transmission, the allowed bandwidth assigned to your account. Alternatively, other than Wi-Fi, you also can use a cellular network. That's also called a wide area access. So just to give you some idea, so a lot of you guys have 4G on your cell phone. The network bandwidth is between 1 to 10 megabits per second. So the reason is this router, the Wi-Fi used by a cellular network need to cover a much wider range. For example, typically a cell phone tower can cover tens of kilometers of area. Our Wi-Fi only covers about 100 feet. So that means a single room or a single house. So this is really the trade-off between the coverage of the Wi-Fi and the transmission rate. I think you heard a lot about the 5G. So the 5G bandwidth is about 10 times larger than the 4G. That means 10 to 100 megabits per second. So then you can really get the Wi-Fi level of performance on your cell phone. So when you have a laptop or cell phone connected to a network, the host really sends a packet of data. So So the host will do these things. First, you will send a application message. Then you will break the message into small chunks known as packets. And we can quantify the size of the packet by the length in the bits. So this is so first you will ask, why do we need to break a message into packets? So think about it this way. If I need to send a large stack of papers, I say we have 1,000 pieces of paper, and you send it to someone in Tulsa through the post office. As you can see that if I just package it like a huge box, it will be very hard for the post office to handle. So you need like 2 persons to lift that. Instead, I can separate that like 1,000 pieces of paper into small books. I can staple those pieces together. Maybe I have 10 pages or 100 pages per letter. And that would be much easier to handle. So the same idea is here. Basically, if you have small packets, it's easier for the network to send over the network. And when you have a packet to send, the packet will be sent over the link through this transmission rate. So it's typically designated with a letter called R here. Then we can think about we just talked about the packet of size L. And also we know all the communication has a bandwidth of R, bits per second. So you can calculate a transmission delay. So you just need to take the number of bits, divide by the bits, the number of bits you can send per second. So of course this is called a packet transmission delay. One thing I need to remember is this is just how much time it's like take for you to push those bits into the communication link. It doesn't tell you how fast this bit will arrive at destination. It's just a matter of how fast you can jam those bits into your communication link. So if you have a wider bandwidth, that means you can jam more bits per second. It still takes the speed of light to arrive at destination, right? So now we talk about the end systems. Then we can switch our focus to the core. What is the core of the internet? It's actually performing the network switching. So the job is mainly to forward packet from one router to the next. So let's say you have a bit, you send those packets to a router. Then the router needs to look at what's the address, what's of the destination. Based on the address, this router will send that packet to the next router. So for example, let's say we need to send a packet to Seattle. We send a message to a post office. The post office may send that packet first to a sorting facility in Dallas. Then when Dallas sends the package, then Dallas will decide to send to the next stop, maybe San Francisco. Then through these few hops, it may reach a destination. So the network core is doing all those forwarding services for you. And each post office, each of those sorting facility is basically a network router. So how does this package get sent inside this router? It's actually sent as a stored forward fashion. This is an example here. So let's say you have broken your message into 3 packets, and you have this link here. The first packet will be sent over this link. Then this link will be transmitted as R bit per second. When the router receives it, it actually doesn't, it will take a certain time to receive this, right? You actually need to receive the whole packet before you forward this packet onto the next router. So if you think about it, one alternative way is if you are a router, you receive the first bit, you just forward the first bit. When you receive the second bit, you just forward the second bit. But actually, this is very hard for a router to do. Instead, the router will receive the packet in the entirety, then send it on. You can think of this as a quantum action. Basically, you can either receive a whole packet or you don't receive the packet. You either forward the entire packet or you don't forward the entire packet. So it's one unit, one atomic action. And then we can do a calculation. So let's say you have a packet that's 4.5 megabits in size. And the link, the bandwidth of this link is 4.5 megabits per second. That means you can push 1.5 megabits into the link per second. If you take this number, divide this number, you have 5 seconds, right? That means the transmission is 5 seconds. It takes 5 seconds for the host to push all the link into to this communication and into this router. After this router receives the entire packet, you take a look at the destination address, and it will decide where to send next. In this one-hop example, the router will have a direct connection with destination. They will send it onto the destination. So remember, we have separated the message into multiple packets, right? Then you can also send the next package. This packet has nothing to do with each other. For example, the next packet may be sent to a different router. This router may use a different route to reach this destination. So packets are basically a separate unit of communication. And I want to ask you, let's say if we don't consider the propagation delay, how much does it take for the first packet? How much transmission delay do you have from the source to destination? 2, right? Because it takes 5 seconds for the entire packet received in the router. After the router receives this message, it pushes through the semi-communication link. So this also takes 5 seconds to do the transmission. So in total, you have 10 seconds of transmission delay. So remember here, we have to consider the actual time for transmission between this. So this is, we'll cover this later. This is called a propagation delay. So now I want to talk about a different delay. So remember, all these end hosts share a router. Let's say in your apartment, you have 5 different roommates. You are all watching Netflix of different shows. And then all these different packets need to arrive and need to be shared among different systems, different devices in the home network. And then you share the same router. So in this case, let's think about an example. You are all trying to upload a big video to the network. So let's say you have a very good router. The bandwidth between your end system and router is 100 megabits per second. However, you guys are very cheap on the cable bill. You booked a very low level bandwidth service. You only have 10 megabits per second to the Comcast head office. So what would happen? Let's say A and B, they're all pumping data into the router as 100 megabits per second. But only 1 megabit per second will be pumped out of this server. So as you can imagine, in any situation, we have a line. So just like if you go to checkout, if there's more people coming in than leaving, then you have a line anywhere. So similarly, all these packets will form a queue inside this router. So for example, if this situation lasts for a second, you will have 90 megabits of queue in this router. So let's say that this situation lasts for only 1 second. Then both A and B decide to not send to any bits anymore after this 1 second. Then you will take 90 seconds for this router to clear up this queue. So in that case, you will not have any problem. But imagine that if you are both whole system together keep pumping 100 megabits per second into this router, after 2 seconds, you will have 180 megabits accumulated in the buffer of this router. Of course, your router don't have an infinite amount of buffer to store the message. Then what does the router do? It simply drops packets. So it just sends those packets to a black hole, pretend it didn't see it. So this is the only way they can handle this kind of excessive delay for the later coming messages. So this is where you can often see that buffering if you're watching a YouTube video on your cell phone. So basically, either packets are being lined up in a certain router, or it's being dropped. Another way is if you are downloading a map file, YouTube video over a week, low bandwidth communication, it will automatically degrade to a lower resolution. Is to save bandwidth, so you have less congestion and less number of lost packets in the router. So of course, we just talked about router is actually very, very important in the network. It's basically the gatekeeper to the internet. There are actually 2 functions performed by the router. One is called routing. Basically, it's a lookup table. If you imagine you are a sorting facility in a post office, if you see all the packages, they just decide where to send the next. This is a routing table. You often hear the word IP address. All the host has a unique identifier. That's identifies the IP address. It basically looks at the IP address and decides where to send the next. this is basically an output link. Let's say this router has 3 output links, 1, 2, 3. This lookup table will just look at what's the IP address and send to the output link 1. And if this is the header value for the IP address, it will send to the output link 2. And the forward function will actually do the forwarding. And this is done in very fast, like a nanosecond per time frame. And the routing table may be updated in minutes or hours. So this is updated by the network controller. For example, if it senses a conjunction in some network, it can route the packets to other alternative routes. So here we will talk about the big idea, one of the big ideas in the internet. That's the switching.
Does the routing determine the entire route or just the next step?
Next step. So one router only has a local view. Of course, if you are a network operator, you would control over thousands of different routers. So you would need to coordinate between these routers. By the way, if you have any questions, just stop me. So I don't want just to keep talking and then you guys get confused. If I lost you, that's not the point. So we talked about this packet switching idea. So actually, this alternative idea of building a network is called circuit switching. So actually, this is a network that used to build a telephone network. I don't know if you guys still use, anyone used to use landline anymore. In landline, you actually can get a busy tone. So if you dial a number, and if that number, this line is occupied, you won't be able to dial it in. So that's because if you want to communicate between one system to the other system, you actually need to reserve a dedicated channel between those two systems. So for example, in this router to this router, you may have 4 different channels. And from here to this router, you have 4 different channels. If you use a circuit switching design for a computer network, if this computer needs to talk to the other computer, you need to first talk to the network operator. You need to first reserve a channel in this hop, then reserve another channel in this hop. Only after you reserve this dedicated communication link, then these 2 computers can start to talk to each other. So this is used very often for if you have a need for dedicated bandwidth, like a telephone network. Then how do you implement this circuit switching? If you have a link, communication link between 2 devices, you actually have 2 domains for you to play with. One is frequency, the other time. So let's say you talk to the other whole system for an hour. One way is to divide by the frequency. Each user have a different band of frequency that I can use only for that user. In that case, let's say we can divide this frequency into 4 bands. And of course, you can control how wide that band is. The wider that band is, the more transmission rate that user will have. So this is where the bandwidth, this term comes from. So why is often used to refer to the transmission rate? It comes from this way of dividing a communication link by frequency. So by doing this, you can multiplex multiple communication channels or one single physical communication link. There's another way to do that. That's called a time division multiplexing. So in that case, you divide the time on this link by user. So basically, the first user may have the first second of use the entire bandwidth of the frequency of this communication link. Then you will give up the entire channel to the second user. So you can imagine that first user send a few packets, it switch to the second user can send a few packets. So you can do a round robin going through the user over and over again. So this is another way to do a multiplexing over a single communication channel. So let's walk through a few examples to get a concrete idea of what's the pros and cons of packet switching versus the circuit switching. So let's say you have a link. The transmission rate, the bandwidth is 1 megabit per second link. And then you have a few users. When they are active, they will send messages at the rate of 100 kilobits per second. But they are only active for 10% of the time. So if you do a simple division, So basically, you divide this link over this user. Each user needs to have a guarantee of 100 kilobits per second. Then that means you can only support 10 users. Right? If you have more than that 10 number of users, you cannot divide that frequency or time more than 10 pieces. However, if you use the packet switching, you can support up to 35 users. So the reason for that is there's no magic around. It's because you know that these users are not active all the time. They're active only 10% of the time. So in that case, the chance of actually getting more than 10 active users at any given time is only less than 0.004% of chance. That means the chance of congestion is very, very low even if you allow 35 simultaneous users on your connection link. So is this, so packet switching, of course, can support more users, but there's a drawback. So first, usually use packet switching only for bursty data. When we say bursting, that means, for example, you are writing an email, then you are spending 10 minutes to write that email. Maybe that email will take only 1 second to transmit. There's no point for you to have a dedicated link to that. Or if you are trying to browse the internet, you click a link, the server will send you one web page. So that is the only time when you're using the bandwidth of your connection. The rest you are just browsing actually looking through the net, through the web page. Then you come to another link, you click that link. Then the server will send you another page. So we consider most of the internet users to be very bursty. So this allows different users to share communication simultaneously. And also it's very simple to set up. As I mentioned before, to circuit switching, some network controller need to build up dedicated link. That's very complicated. It's not very scalable. But with this packet switching, it's much more scalable to billions or trillions of devices. Now, of course, it's possible to have congestions. So as I talked about before, when there's congestion, you'll see congestion in your router. You will see delay, and you will see loss of packets. So this is a trade-off that the internet designer has decided to make in order to make a scalable network. So you have to tolerate some degradation of service in terms of bandwidth, delay, or the loss of packets. Of course, that's also changing a little bit because the internet are being more and more often used for real-time application. Let's say you want to do a conference call with someone. If you experience substantial delay, that will degrade the service. Or if you want to watch TV on the internet, you also want to guarantee the bandwidth, right? So that's actually not what internet is designed originally for. Internet is designed for bursty data. So how to solve that problem is still an open question. So of course you can, if you want to design a network, you can do this way. You can label different packets with different priority. If you see this packet is for email, you don't mind a minute of delay to send that email. Then you can have a much lower priority. If you see this packet come from a video application, from Netflix or conference call, then you can assign a higher priority. Then this packet will experience less delay over the network. This is analogous to the boarding system. If you guys know, usually when you try to board an airplane, you have a priority lane and an economic lane. So usually even the boarding agency will open up the economic lane for everyone to board, so you have a long line there. But if you have a first class ticket, you can skip that line and then jump direct to the head. And the boarding agent will give priority to those first class passengers, right? The first class will not experience any delay. Essentially, we can do the same thing to give you a good quality of service based on what kind of application you are running. But at the same time, this runs into a gray area. This is where we're going to talk about net neutrality. So of course, it's a good intention for you to prioritize video packets because you know it's really time sensitive. It's good to deprioritize emails or text files. But then what about Google pays a network provider? I will pay you like $1 million a year. When you see the packet from Google, you want to prioritize over other startup. Then in that case, if you want to try to start the next Google, the service you provide will be much slower than whatever packet is coming from Google or Facebook. So in the current, the agreement is the internet should be neutral to all the parties. to avoid this kind of discrimination or paying to get a higher bandwidth. But still, we can see the generation products packets. So that's still an open question and an unsolved problem. So, okay, so I think this is where we can end today's lecture. So on Wednesday, we'll continue from this point. Okay, that's it. Thanks.
Awesome.